Hello, everybody. We are going to do what, I wish I had more time to make more of these, but we're going to do a homework help video. That's what I think we'll call this for kinetics, because in your homework, I assigned quite a few graphing activities, at least 3 or 4. I thought there were only 2, so I think we'll go over how to set up one of these, right? I'm going to walk through this on Google Sheets. You can use Excel if you prefer. The setup's going to be the same. We'll look at some tricks. Maybe we'll do it in both. We'll see. We'll look at some tricks to maybe get some more sig figs out of our regressions, just because depending on the value, you might get one sig fig out and one sig fig is not enough to do math with. So here we have a homework problem, right? Context here doesn't really matter. We look down here and we are shown data in the form of a table and asked to find the first order rate constant. So it's very nice of them to tell us this is first order. We can go through and show how we would do this if we're not told that. But that does save us some trouble. We're told the temperature here, which we don't need. But anytime you get a table of data, there's really only 2 things that could happen. A, you have one of those kinetic, what's the order of this reaction rate law type questions where you're comparing between trials. Okay. If we're in kind of this integrated rate law or even Arrhenius equation side of things, we're going to have to plot this. And we might not plot it in the form it's in. Statistically, we're probably not. All right, so we're told here time and we're told concentration. And we should be clear that these little brackets here mean concentration. All right, so this is the concentration of aqueous whatever. We are not told a unit of concentration here, which is kind of funny. I would assume it's molar, but we're not told it. Because we're not told it, I'm going to assume it doesn't matter. Right? It means we don't have to do any unit conversions. So I'm going to take these values. I'm going to put them on my clipboard. This won't end well for me though. So we're going to put it down here. I'll just tell it to take the values. Notice that these are not numbers, right? When I put them in, it brought over this X. X is a letter as far as Excel is concerned. So this is not numeric data. And also notice that 10 to the minus 3, these exponents didn't transfer over well either. So I'm going to have to reformat these so these are real numbers. All right, so I'm just going to take my header over. And now I'm just going to take 1.08 e to the minus 3. All right, so now I've just taken this. E is our engineering notation that lets us put these in. We could also do it regular, so we could do 7.77 times, right, my little asterisk sign, 10 to the minus 4. All right, that would work as well too. And we're just going to do that for all of these. There are ways we could do this with formula, but like they would be dumb and not worth your time. If you had a lot of data like this, maybe, but we're not going to worry about it. So now we have our numeric data. We really don't need this column anymore. I will delete it just for convenience. So now these are hopefully in our correct molar concentrations. Let's say this problem didn't tell us this was first order. All right, we are only concerned with 0 first and second order problems in this course. So we would want to plot each of these data sets according to whether we think it's 0 first or second order, which means we would need to plot concentration versus time, the natural log of A versus time, or 1 over A versus time. All right, we can go back and look through those derivations, right? We just take our integrated rate laws, we take their linear forms, we map them to a linear regression, y equals mx plus b. So our 0 order is just as is. We don't have to do anything fancy there. Our first order, we're going to take the natural log of whatever that thing is, we'll call it x. And our second order is going to be 1 over x. Now I'm just going to do a formula here. So equal natural log of that guy. And then I will accept the autofill. And we're going to do the same thing. We're going to do 1 over the concentration. If I don't want to do the autofill, I can hover over this bottom right corner and I can click and drag it, or I can double click it to extend it all the way down. Either one is fine. And now I have potential options, right? So I have my time versus concentration. This would be 0 order. Natural log, this would be first order, and 1 over x, which would be second order. All right, we already know that this one will be the most linear, but why don't we plot all of these? When I plot all of these, let's just see what happens. I'm going to do insert chart. I want a scatter plot, and these are wildly different axes, right? So it doesn't make super great sense to put these as 1, but that's okay. And then I want to turn on labels for these, right? There we go, trend line. So we'll put on trend lines for each of these. Get our R squared on there so we can see that. I have no idea how we're going to click on our blue one. Okay, there we go. There we go. There we go. We can tab through that. Show R squared. All right, so now we have these trend lines for these 3 things. we can see from the r squared that this guy right here, natural log of x, has the best r squared. It's closest to 1. So we would predict from this data that this is a first order reaction, which again is what the problem told us, right? Why don't I have the label? Oh, I have to turn on equation for that. All right, we'll turn on equation for all of these. There we go. So now we have equations. It looks like Sheets is trying really hard to show me all of the sig figs here, which is nice. I'm going to open Excel real quick. All right, so if you're doing this in Excel, we'll just put these over here. We would do the same thing, right? We would highlight all of this, insert, scatter plot. Do not ever put the connecting lines on your scatter plot. I personally despise using Excel to graph things. I would much rather do this in Jump because Excel's really not that great for graphing. That's what I want. Select data. All right, I guess we'll just have to do all of these manually. What a pain. What a pain. And okay, apparently you don't like those in there. That's fine. Can I put a name in here? Guess that's 0 order. We have first order. Nothing about this pleases me. You see how much easier this was to do in Sheets? Which I assume just means I did something wrong, but like, you know, my expected behavior is if I select a whole bunch of things, I have an x-axis first and then a whole bunch of y-axes. All right, there we go. Now this looks like what we saw in Sheets. Great. We're going to add that trend line. We're going to display the equation there. We're going to add this trend line. We're going to display that equation there. And I don't know how we're going to click on our 0, right? Excel had a nice option for us to select our series. All right, so we want the series 0, and we want to add a trend line. How do we do that? Oh, this button, right? Add trend line. There we go. And then I guess we're just going to have to go into this again. 0, trend line, option, display equation. Okay. So now let's just arrange these. Nope. And this is why I wanted to do this, to show that sometimes you will get very bad sig figs out. So like this one has 5 sig figs, this one has 3 sig figs, this one has 1 sig fig down here. And if you try to do math with this, you will get very bad answers because we don't want 1 sig fig math, right? Sheets spared us that, right? It correctly interpreted this as scientific notation and gave us 3. So for Excel, what we're going to do is we're just going to go over to our label options. We're going to change our number type to scientific. And now that will force this to report this with 3 sig figs or 2 decimals of accuracy. All right. Yeah, this will be 3 sig figs, right? Because it's in engineering notation. All right. So now we have our values. Again, we knew from the get-go that this was going to be first order. All right. So our first order equation has the best r squared. Sheets did this so much better, right? There are good things about Excel. You know, you have more customization options with your graph. Personally, highly recommend learning how to use Jump if you want to make really cool graphs, but potato, potato. All right, so now we have this data. Another way you could do this is, let's see, we could do equal linest. So this will do a linear regression, a linear estimate of your data. We select our y values, we select our x values. We want to calculate the b value as normal, so we're going to set that to true or 1. And I guess we can return additional regression statistics. All right, so this tells us a couple things. All right, this is our 0 order regression statistics. Let's see, let's change this to scientific, just so we make it clear, right? This is that slope. This is the intercept. We don't worry about these guys. These are standard errors on those or something akin to that. This is your r squared value. So why don't we highlight these? These are good. This is informative. We don't need anything else in here, right? One of these, I think this is an F statistic maybe. This is your degrees of freedom, whatever. We could do that again, right? But now instead of that being our y data, we do that. So this is another way that you can get out that data from your linear regression. Right, notice these line up with here. It's the same command in Sheets too. We have linest, it's the same format. This will be a very common theme. All right, so same exact numbers here. This is the first order regression. And that should make sense, right? That these should be the same number because these are the same data with the same processing. Sheets goes a little wacky on the these things, right? On the sig figs. So we can probably round that somewhere. But so where do we go from here? All right, we've now found this is first order. I'm never opening Excel again. So that was it. That was your Excel journey. Just gonna do the rest of this in Sheets. So we know that for a first order reaction, that the slope of our linearized rate law is equal to negative k, right? So m is equal to negative k. So our slope here is just going to be this number, but positive, right? 0.0349. And boom, we're done. Now, we could have another extension of this question. They could ask you what's the concentration at a specific time. So like what's the concentration at t equals 15 or 35 or 40? If you know your k value, you know the initial concentration, you're told T, you can find your concentration at a later temperature. And this is something that you guys will do some variant of in lab. It'll either be this one or the Arrhenius. So why don't we look at this again, but for an Arrhenius question. All right, so here's an Arrhenius question. And this is what we did in 06B, assuming that's when we did this. But we're given raw temperature and raw rate law data. We're going to do the same thing. We're going to bring this over into a sheet. We are going to have to clean this up, right? Because right now this says 4.14 x 105, which is clearly not correct. So we're going to do 4.14 e to the 5, and we'll just do this for all of them. And hopefully I won't mess any of these up because that happens a lot. Yeah, we'll leave this column, whatever, doesn't matter. All right, so for the Arrhenius equation, again, so as a reminder, we have a data table here. That's a hint that we probably need to graph this. And the hint here, the reason we graph this is we're given lots of data, right? We don't want to base our analysis on 2 data points. That will not get us a good answer, nor will it get us the right answer. So we want some analysis that leverages all 5 of these at once, and that's where these graphical analyses come in and the linear regression. All right, so we have the linearized form of the Arrhenius equation, which says if we plot the natural log of k on our y-axis versus 1 over t on our x-axis, that we can find these other values, right? Our slope then becomes negative EA over R. Our intercept becomes B. So let's go look at that over here. So we want 1 over T in Kelvin. So do a quick check, make sure that this is in Kelvin. I guess technically this would be K to the minus 1. And then we're just going to, again, write our formula equals 1 over, and we're going to click our first cell there, and we're going to apply this all the way down. So now we have 1 over t. We want the natural log of k here. Weird fact is that when we take the natural log of things, we kind of assume the units disappear and then they magically reappear later if we undo that, if we exponentiate it. So now we have 1 over t versus natural log of k. This is in our linearized form, right? X versus y. I have my x column, I have my y column. I'm just going to do insert chart. Why is that not linear? Why didn't this? I forgot the ln. All right, that's why. So I just plotted the wrong stuff there. There we go. Nice and linear now. I don't know why. Again, doesn't really matter what our values are here. We can use the graph to get the trend line if we want. Use equation. And we can also do our ln est if we want. Why don't we put it down 1? All right, we have our y values, our x values, 1, 1, end. All right, so now we have some information here. We have our slope, we have our intersect. We really only technically need the slope for this one. The r squared is nice to know, but we don't super need that. Let's get some reasonable sig figs here. This one we will just round to 4. It's actually a really hard question of if you take a linear regression, how many sig figs do you report on your slope? Because it depends on how good your r squared value is. So r squared, our r squared here is very large. So we can probably report a lot of sig figs on this, right? If I were to multiply this times 1 minus this, why did that come out? Oh, because this is negative. Don't worry about that. So we have accuracy on this to like a scary number, right? Like to the thousandths place. We could probably, I would not do this. We could report this to 6 sig figs probably and be safe, or 7, right? Because this would be this number plus or minus this amount if we read our r squared as percent like predictive power. But we don't need to worry about that, right? We're not that kind of course. So this is our Arrhenius result. this value here, negative 2451, we are looking here, is equal to negative EA over R. All right, so we know R is 8.314 joules, capital, per mole Kelvin. We know M is this negative 2451. It is unitless, I think, right? No, it'll have units of Kelvin, right? Because we want to cancel out the 1 over K on the bottom. Not a big deal. So if we say M is equal to negative EA over R, that's the same as saying EA is equal to negative M over R. This is a multiply, right? We cross multiply. Take that value and we're going to multiply it by 8.314. So that'll give us an answer, and this will have units of joules per mole. Should be negative, right? We probably want that in kilojoules, so we're just going to take that top number and divide it by 1,000. We get 20.37 here. All right, that'll be that. Now we're told to find the rate constant at 300K. We have a couple options here. One option would be to find the frequency factor, right? We know that the intercept here, this guy, is equal to the natural log of our frequency factor. So our frequency factor is equal to e to the b. And we could do that, right? We could exponentiate this value and get our frequency factor. We'd probably want to report that in scientific notation. And then we could use that inside the Arrhenius equation to find K at a specific temperature, right? We're told to find K at 300 Kelvin. So we know K is equal to A times E to the negative EA over RT. We have our A value times E to the negative this value divided by R. I'm going to be a little careful here. Times 300. Why do you not like that? Oh, because let's put 8.314 there. All right, so we could find K this way, right? We have A times exp to the negative EA over RT. Notice I do have to be careful here that my units of EA and RT match, or EA and R match. So this is joules per mole. This is kilojoules per mole. If I mix my kilojoules and my joules per mole, EA and R values, I will get a wrong answer. It'll be off by a lot, and by a lot. And our last kind of check here is we just want to compare. Okay, so this is 2.05. We can compare 2.05 to this, right? So 300 is higher than this, so we expect it to be a larger value than this. We know that this kind of climbs exponentially, so we expect it to be a lot larger since we're climbing 57 degrees here. So 2 times 10 to the 7, that's a magnitude higher, right? So that's probably okay. I feel okay with that. This is one way of doing this, and this is actually the long way of doing it, right? We already have an equation here that tells us our value of K, right? We have our linear regression, which says the natural log of K is equal to negative 2451 times X plus 25. So if we wanted to be really formal, we could just reuse that. We would say that this number times 1 over 300, right? Because that's our X value, plus this. And that is equal to the natural log of K, right? Mx plus b, where X is 1 over t. If we wanted to find out what K is, we would just raise that to this power, right? And that's going to give us the same number as what we saw over there in theory, right? So both of these are 2.05 e to the 7. Oh, that's cool. Was that there before? Did that just appear when I hit the E button? I think that just appeared. Cool. And then we submit that, and look at that, we're right. Okay. That's the main stuff I wanted to talk about in terms of graphing. I did want to quick remind us how math works here, and particularly that, you know, we are allowed to use Wolfram Alpha and other such tools when we have, and let's rotate this, there we go. You know, if we have our regular equations, our integrated rate laws here, we have our 3 integrated rate laws here. A lot of our homework problems and exam problems will say, okay, here's K, here's A naught, find AT at some specific time. What I strongly encourage you guys to do is set up this equation inside Wolfram Alpha and let Wolfram Alpha solve it for you. All right, we could go through and we could solve this, right? If we wanted to find these as functions of AT, the 0 order one is already solved for us. If I wanted to do this for first order, I would have to exponentiate both sides of the equation to undo the natural log. So we get AT is equal to E, and then the entire right-hand side in the top. All right, so we could do that, and that's fine. Or we could just type into Wolfram alpha, natural log of AT. We could type this entire form in there and just let Wolfram solve it for us. I have no issue with that. We can do the same thing for our second order here, which is also going to be a little bit painful, right? So if we want to solve for AT, we have to raise the entire right-hand side to -1. All right, so we get KT plus 1 over A naught. And that's fine. We can do that. A lot of students, what they do is they don't do this beforehand, right? They find out what this number is, and then they just cross multiply to get AT, and that's fine. You find out what this number is, and then you exponentiate. You don't have to do this all in one step. But because we're allowed to use Wolfram Alpha, because I'm encouraging us to use symbolic math software to help us solve these, we don't need to do any manipulation. We can take the raw equation in its linearized form and just plug it into Wolfram Alpha and go. So why don't we look at a quick example of what that would look like. Here we go. Here we have a pretty basic one. So here we're told we have a second order reaction, a rate constant K. I'm told K is equal to 0.0265 m to the -1, min to the -1. We can tell, for the record, directly that this is second order because of the units on K. So a mean version of this question would tell you the K value, but it wouldn't tell you it's second order, and you would be expected to say, that's a second order equation because of the units on K. And that is a totally fair question to ask on the exam. We are told that A naught is equal to 1.75. What is AT at T equals 180.0 minutes? What I would do here is we would take our linear version of this, because that's what we've seen, and we're just going to substitute in some values, right? We're solving for 1 over T. We're told this value of K, so let's use that. Let's multiply that by T, and then we're going to add to that 1 over our initial concentration. And we totally remembered to write our units on there the first time. All right, so that's all given to us in the problem, and we're just going to turn over to our good buddy Wolfram, right? So we're on Wolfram. I'm going to write this 1 over X since I know I'm solving for AT, 0.0265. I'm not going to write my units in there because it's a little difficult to make Wolfram work with the units. And then 1 divided by 1.75. And we hit enter here, and we get our X is equal to 0.187. All right, and we have 3 sig figs. We submit that answer, and that is correct too. 4 for 4? 4 for 4. Again, strongly recommend symbolic math. Set up your equations, turn it over to the robot, let the robot do the work. Just because there's a surprising amount of sub-calculations to solve these integrated rate laws if you're not converting them into these AT forms, right? And even then, these are messy, right? Like, you have to be very careful with your input to make sure you put these in correctly so that you have the exponents and the parentheses all set up right. If you're doing this by hand or on a calculator, there are many opportunities to mess this up. So this unit particularly, and our next unit, but equilibria and kinetics are where these symbolic math programs really shine. Highly recommend using them. It's good to be able to do these by hand, but you'll notice that I am able to do these by hand and I still choose to use the software, and that's because the software won't let me down. And if I mess up input in the software, it's easy to go back and edit it. I think that's it. I think this is our homework help for kinetics. Hope you guys enjoy it. I hope it helps. I hope you watch this video. If you don't watch this video, you're lame, but by virtue of seeing this, you've seen it. So good job. All right, so enjoy your weekend. Good luck with this. I'll see you guys on Tuesday. Oh, and you have to do all this in lab or for your lab. So I really hope this helps with lab.